This is part one in the lesson about chemical reactions. First semester we spend a lot of time talking about chemical changes, changes in identity. In second semester we're going to spend a bit of time talking about chemical reactions, the actual process by which these changes take place. So chemical reactions, the process by which chemical changes take place. The process by which chemical changes take place. And you'll notice I've put an abbreviation here, RXN for reaction. It's a legit abbreviation. It's going to save me quite a bit of writing. I joke that by the end of the semester it's all hand signals and abbreviations because I get really tired of writing that stuff. So once again, chemical reaction, change in identity, but not a nuclear change. So I think that's important to note that chemical changes, you have some change in identity that's indicated by a breaking or forming of chemical bonds or a transfer of electrons, or both. And we're not changing the nucleus because that's nuclear chemistry, all right? So this is ordinary chemical reactions. Right? They're non-nuclear, which means there's no change to the nucleus. All right? So I had said moments ago that our indications are not our indications, but our main types, our primary ways that we have this change in identity is we have some breaking or forming of chemical bonds. And or we have some transfer of electrons. And that's going to be the basis for how our chemical reactions take place. You can go back to what Dalton said in his atomic theory, that atoms of different elements are different, and chemical changes involve changes in the way in which atoms are bonded together, not actual changes to the atoms themselves. So even that far back, there was a pretty good idea of how these chemical reactions take place. So one of the things we need to consider for real-world chemistry, if we're going to describe how these reactions are taking place in written form, is visually how are we going to identify that these reactions are taking place. So common indications of a chemical reaction are a pretty important consideration. And there's four primary ones that we would work with. The first of which is something simple like a change in color. And a common misconception with this is that a change in color or any of these indications of a chemical reaction are written in stone indications of a chemical reaction. They're not necessarily, right? You could have a change in color due to a chemical reaction like iron rusting, or phenolphthalein, an acid-base indicator, changing color. Or you could have a physical change in color. It's not a chemical reaction, like putting food coloring in water. It just changes the color. You start with water and you end up with water. It's just a different color. So change in color, good indication of a chemical reaction. A really common chemical reaction for people to recognize is combustion. And with combustion, you generally get heat or light transfer. And I put heat or light transfer, not necessarily heat or light given off, because you can have reactions that produce heat and light, like burning a piece of paper. You can have reactions that produce just light for practical purposes, like a glow stick that kids might use around Halloween. Or you can have a reaction that doesn't produce light in the visible spectrum anyway, but you do get heat, like those hand warmers people use for sporting events that kind of look like dryer sheets with a powder in them. And those are generally iron rusting inside of there, and that's an exothermic reaction. Now, you can have physical changes that involve heat and light transfer, like if you heat up a piece of metal. It may glow in the visible spectrum, and it may give off a bunch of heat, but the catch is it's still that piece of metal, like a piece of iron. Another good indication of a chemical reaction, but again, not a written in stone indication of a chemical reaction, is the evolution of a gas. Right? And like, it's science terminology. Evolution of a gas is just a way of saying gas is given off, or bubbles is what I tell my kids. So gas given off during that chemical reaction. And I think that if you look back in your own mind in terms of what things are a chemical reaction, the first thing you might have spotted and recognized as a chemical reaction is the volcano reaction, where people mix baking soda and vinegar and then it overflows the cup or overflows this paper mache volcano or whatever. And in that case, you have the decomposition of a metal carbonate using an acid, but there's bubbles, right? CO2, and that's why it foams over in that case. So that's a classic example where you have evolution of a gas. You could have a single replacement like zinc and hydrochloric acid that we'll look at in a later video. Or you could have the decomposition of hydrogen peroxide, right? Like you put peroxide in a cut and it bubbles. It's releasing oxygen gas as that catalase in your blood decomposes the hydrogen peroxide or speeds that reaction up. And there's plenty of examples of evolution of a gas that aren't chemical changes. Things like boiling water. You start out with liquid water and you end up with gaseous water, right? So we can go either way on something like that. You just got to watch out. And then the last one, which is one that is least likely to be recognized at an early stage, would be formation of a precipitate. And there is a legit abbreviation for precipitate, PPT. It's not PowerPoint, it's a totally different context, and it's not going to come up for me anyway, but formation of a precipitate. And it doesn't have to be a chemical change, and I think the most common context for people is like a chance of precipitation that the weather forecaster might give you. Like, if you were to look up in the sky, you wouldn't see like an iceberg that someone chips ice off of, and that's why it snows. You wouldn't look up in there and there's like a giant cup full of water that overflows, and that's why it rains. Up in the sky we have gaseous water, right? And then it precipitates down, it changes phase, and comes down as a solid or comes down as a liquid. And that's a type of precipitation. And a general idea of how precipitation works is to say that you have some out of phase product, all right? And that's how I'll say it, some out of phase product. Okay? And when we say product, that's terminology we'll define later. A product is just the thing that is formed or the thing that is produced in a chemical reaction. And most commonly, when you see people defining what a precipitate is, you're going to have a situation where you have an aqueous solution and an aqueous solution producing a solid. And we'll have to deal with aqueous here in a minute. Usually you have some aqueous and something aqueous giving you something solid. All right? And so aqueous is obviously a term we're going to have to address right away as well. So when you look at the word aqueous, I think most people, it's pretty intuitive to say aqua, there's water involved, right? So aqueous, and as we abbreviate that, that has AQ for its abbreviation. When you have something that's aqueous, it literally is in water. And there's a couple different ways we can think of this, and there's an important distinction that I want to make. In water generally refers to dissolved in water. So if you take sugar, like a sugar cube, it's a solid. You have all kinds of sugar molecules held together by intermolecular forces. You put it in water, and those sugar molecules spread apart, right? They dissolve into the water. So if you put sugar in water, you get sugar water, which has all those sugar molecules, and they are farther apart from each other. And that's a key distinction, all right? So you can dissolve, which is a general term for separating, overcoming intermolecular forces. And that's an important term in the big picture that we've covered before. All right. So you have things like dipole-dipole forces or hydrogen bonding or London dispersion forces that are pulling particles closer together. And when you dissolve something, the actual particles, in the case of sugar, molecules get farther apart. And that's all that's going on. And then there's a subcategory of dissolving that we would say is to dissociate. And I think it's pretty straightforward to look at that word and say, a associate, which means to make some connection to something. So to dissociate is to separate, right? And specifically, we're overcoming ionic forces, which are intermolecular, and we're turning those ionic compounds into ions. So in this case, we are separating our ionic compounds into ions. All right. So unlike a case where like sugar molecules just become farther apart, like table salt composed of sodium ions and chloride ions, literally those ions get farther apart. So while there is sugar in sugar water, there's not actually any salt in salt water. That NaCl dissociates into sodium ions and chloride ions.